Page 16. So I'll tell you what's happening. I always like to tell you what's coming down further down the line. So this is page 16. Unfortunately, it cut off, right? But it's page 16, compound interest. We're going to start with the formula for compound interest, but then later, and I use it to this day, okay? We're going to use, when you go to apps, we're going to use the finance function quite often. Something called TVM solver, time value money. You don't have to worry about it today, just yet, right? But that's where we're going. And soon, if you go into TVM solver, you can calculate anything you want based on any payments, monthly, bi-weekly, semi-monthly, whatever. You can use this to figure out, hey, if I borrow this much money over 5 years at this interest rate, what would my payment be for that car, right? I still have it on my phone. Like I have this app on my phone. So I use it quickly if I want to figure out, hey, how much would this cost me? How much interest would I be paying? All of that stuff. It's a very powerful app. So right now, we're just going to use the formula, and the formula is limited. We can't do a whole lot with it, right? But I need you to understand that this is what's happening in the background of that app, right? Okay, so if you have highlighters, get them ready as well. Okay, so compound interest. How is this different, right? Compound interest is the interest earned on both, right? So it's interest earned on both the principal and the accumulated interest. That's how it's different. It's going to grow faster on you, okay? Most financial institutions, banks, credit cards, credit unions, you name it, either pay or charge compound interest. You're like, what about simple interest, Mr. Erickson? It doesn't. I don't know that it's happening very often. It's more used to estimate, more so. But compound interest is where it's at. Compounding periods refer to what is compounding periods? The amount of times the interest is calculated in a year. Very important to know that. Okay, so if it's monthly compounding, that means that it will be calculated 12 times a year. So it's daily. Credit cards do daily compounding. So they calculate the interest every day. Every day you owe money past the due date, they charge you interest. Okay? When you see the keyword compound, you cannot use simple interest formula. Okay? Do not, if it's compounding periods, and I kind of warned you about that, do not go simple interest, just period. You can't. Okay? Those formulas do not work for this scenario. I'm going to use a different highlighter here. Okay. When this is there, you cannot use simple interest. Okay. I don't know. Use a different color that it stands out, right? Since you're earning interest on previous interest, it creates a snowball effect. Right? It grows slowly, but then as time goes by, as you roll it, so to speak, it will grow bigger and bigger and bigger quite fast. Okay, your investment will essentially grow faster, and similarly, your debt will cost you more. Right? So if you're earning compound interest, you're happy. If you're paying, you're not happy, right? Because it affects you that way. The banks are happy. So I just want to, this one here, therefore, the relation between time and money is exponential when it's compounding. So if you do compound interest, if you compare time and the amount of money you have, it will look like this. It will be a curve like that. Whereas simple interest, what kind of relation do we have with simple interest? Anybody remember? Anybody awake for that? Simple interest. you can be guaranteed that either on an AC quiz or test, this kind of question is going to be asked in some way, shape, or form. So simple interest, it grows at the same rate. So it's actually just a linear growth versus compound interest is exponential. At first, they're very similar at first, but as time goes by, 30, 40, 50 years, there's a significant difference in simple versus compound. Okay. In general, we start with the investment, which is the principal and expected to earn interest. The value of the investment after a period of time is called future value. Nothing changes really here, right? Principal is the initial, future value is obviously what we expect to have at the end. When interest is compounded annually, important, only when it's compounded annually, or per annum, right? You're like, what's that? Legal documents have this wording, but it's really just per year. Okay, don't let's add that here. Per year, same thing. This is what the formula would look like. This should kind of remind you of the exponential function formula. It should remind you a little bit of it. When this number inside here is bigger than 1, what kind of exponential function was it? Increasing or decreasing? If this is bigger than 1, we had an increasing, which is what we expect to happen to money, right? So it's 1 plus the interest rate to the power of time. However, this is the only time I'm going to show you this formula. I'm actually not going to use this one, so I'm not even going to highlight this one. But when the compounding periods change, it affects both the interest rate and the exponent, which is time. Okay. We use the following version. This is the one I want you to have on your. This is the one right here. I don't know how you want to make that happen, but I would just say, hey, that this formula right here should most definitely find its way into your formula sheet. And how is this different than this one up here? What's the difference? Look at R. There's just rate here, but over here it's rate divided by N. What's N again? It's the compounding periods per year. How many times you calculate the interest in a year. So whatever interest rate is given to you is usually a yearly interest. So you need to divide it by the number of times you're going to calculate it that year. Similarly, time, right, is going to be affected by the compounding periods. Because if it's calculated 12 times a year, let's say time was 10 years, right? And it's 12 times in a year. So that would be actually 120 calculations that would have to happen, right? And you're like, well, why wasn't it up here? Well, imagine the N up here would have been 1 because yearly compounding, and N next to this T here would have been 1 as well. That's why this formula just simplifies to that. So I don't want you to use this one. I just want you to stay with this one because you can just plug in that 1 and it really just changes to that, right? So just focus on this. A is the future value or value of maturity. P is the principal, initial amount. R is the interest rate. N is the compounding period per year. How about we give that a special treatment there, right? Because that's how things change. And time is in years. And this one, I would never have to add this to my study sheet. I don't know, I just remember these things. Maybe because I've been teaching it so many times, I just don't forget these things. But if you feel like you need to, like if it says monthly compounding periods, I'm pretty sure all of you would know it's 12 times a year. But I think when students get in trouble is that when it's weekly, like it's weekly compounding, you need to know that it means 52 in a year, right? Semi-monthly, that's 24 in a year. Semi-monthly means twice a month. Let's add that here in case the wording shows up like that, twice a month. So add that, please. Semi-annually, it's twice per year. Right? Weekly, no big deal. Quarterly, I would also think that most of you be like, yeah, that's just 4 times a year because it's quarters. Bi-weekly, if you remember weekly, bi-weekly is twice, two every second week, right? Let's write that down because I know one question every second week. Did you know that by law you need to get paid every second week or twice a month, right? That's why most places pay you twice a month or bi-weekly. You're like, bi-weekly and twice a month is the same thing, Mr. Dirksen. It's not. Twice a month, right? You would get 24 paychecks in a year. If you get paid bi-weekly, you get 26 paychecks in a year. There are 2 months in a year where you get 3 paychecks. Have you ever noticed that? I certainly did when I was younger. Those were good months, right? But still, like if you average it out, it doesn't affect, but it feels like that month you're making more, right? Okay, so we got that figured out. So you need this formula, and you need to know your compounding periods to be successful, right? Because if you don't, then you're gonna be off. Let's do some math with this formula. So let's go over to page 17. Page 17. Let's put that on top there. And oh, just a note. The simple interest homework, I actually made a video. I didn't quite do every single question on it, but if you need help with simple interest, I actually worked through the whole thing and I posted that video so you can go and look it up, okay? Okay, so Greg is 15 years old and inherited $150,000 from his grandmother. He would like to invest it so he can use the money to purchase a house when he turns 25. He has the following options. Option 1, a 4.5% rate compounded monthly. Option 2, same rate, but this one is compounded semi-annually. We're going to calculate the future value for each option. Okay, so let's go ahead and do that. I'm going to do them side by side, right? So this is option 1, and this is option 2, of course. And I'm going to do option 1 here. So I don't want to rush, so I will just do this. I have to use this formula. Notice that n shows up twice, right? I have to use that formula. Why? Because it's compounded, right? Watch here. I'm going to figure out my time. And we go age 25 to age 15, right? We subtract that. That's 10 years. 10 years. And what's n in this case? Compounding periods. If it's monthly, n is 12, right? Because it's monthly. So you figured that out. That's very important to figure out right away if it's not explicitly stated, right? So let's go ahead and calculate that. So this is actually A here that we're doing, right? Calculate the future value for each option. So under option 1, let's plug in and go. The principal is 150,000. And then it's 1 plus the interest rate. I think it goes without saying that we need to turn that into a decimal, right? And then we divide it by 12. And then we go n times t in years. So it turns out to that. So here you want to grab your calculators and kind of, I will give you a little bit of a, I don't know, method of typing this in and showing your work in a sense. So I go like this. Okay. I will figure out what this is inside here. So I usually start with this portion right here. Let me clear my screen first. 0.045 divided by 12. I hit enter. Then I add the 1 to it, plus 1. Can I tell you something? This will sometimes give you a scientific notation, e to the negative whatever. Just add 1 to it and it will solve the problem for you. Okay, so I go 150,000, 1.00375. If this is a very long number, we'll just go dot, 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 right? This one is very easy to do. 12 times 10 is 120. And before you just blindly go and solve this, I want you to understand what's happening here. The interest rate has been split up into 12 chunks because you're using this interest rate as a yearly rate, okay? So we always need to divide it by the compounding period. So you end up with 0.0375 every month that's going to be used. We add 1 to it because this is growing, right? It's growing this money. And over the 10 years, if it's compounded monthly, there will have been 120 calculations that will have been completed by the end of the term, right? By the end of this investment. So I need you to understand that, right? I will make an arrow here, 120 calculations over 10 years. And I'll put like a little bubble around that, right? And now I grab my calculator and I will just take that answer and then raise it to the power of 120. Just this, I just use that number in bracket, raise it to the power of 120. And I actually show this work because if you make a mistake, I've got nothing to go by. And I just go like this. Notice that the exponent is gone. It's now this because I've raised it to the power of 120. And then you just take that number and you multiply that by the 150,000 that's in front of it. And so in 10 years at that interest rate, you now have 235,048 and 92 cents. You have to round to 2 decimals when it's money. Okay, there's no option. You have to give me 2 decimals, right? So that is the future value of that investment compounded monthly. Now, I'm going to pause here. You're going to write this down, make sure it's down. You're going to do the same thing that I've just done here for option 2. Option 2, okay? Use the same formula, right? If you want to, it's not a bad idea at first to keep writing down the formula. You know why? Because it will kind of just stick. You'll be like, oh yeah, I remember the formula. I remember where n goes, right? And so I want you to calculate that, like go back to option 2, right? It has a different compounding period. The time is still the same, right? So plug in everything into this one and calculate the final amount just like I've done on the left side. Go for it. Don't be scared. It's an eraser. That's all you need if you make a mistake later on, right? So let's see. It should only take you a couple minutes. Okay, while you're doing that, just a little heads up. It could be that time is a decimal, like 4.5 years, whatever. It doesn't change a thing, okay? We still do the same thing. We just multiply these two to get that. So in this case, over the 10 years, there will have been 20 calculations done, right? That's important to note here. And so I just take that, raise it to the power of 20. So I get 150,000, 1.56, right? So I made 234,076.38. That's what you should have gotten. And you should notice, right? About $1,000 less here in this scenario compared to that. A bit less, right? But you should see that more compounding periods. If all else is the same, obviously everything else has to be the same, rate, time, everything. But if all else is given and it's the same, then more compounding periods will result in more money in your pocket. So if it's daily, it'd be even better. Okay, daily is 365 times a year. Is that on there? Oh, I'm expecting you to know that. You know that, right? I don't think I have daily on there. How could I have missed that? Can you just put down daily is 365 a year on the previous page? I don't know. Some of you might need it. Some of you are like, Mr. Dirksen, are you kidding me? I know my days in a year, right? All in. You're doing okay. But I'm just gonna add that somewhere because daily does show up, especially when we do credit cards. Okay, A is done. Calculate the interest earned for each option. So we're going to do that. So remember, interest is just taking the final value minus the initial, right? So we'll just go 235,048.92 minus the 150,000, and so I will just, for the time's sake, I'll just get you these numbers. Okay, just write it down. So that's the interest earned for option A. We'll do the same thing for option B. And if you want to beat me to the finish line, you just go ahead and do the rest as well, right? 84,076.48. That's the interest earned for that second option. C is asking me for the rate of return in each option. And I'm just going to use my interest because I already figured that out. And just go divide it by 150,000 times 100. I will also give you that number because at this point I quite frankly think that you should be able to calculate that no problem. Same thing with the second option. We're comparing the exact same initial amounts to the various interest earned, so obviously the second one is not going to do as well as the first one, slightly less, but it does make a difference in the long run. And then D is asking, what can you conclude about compounding periods and the effect on the future value? I will just say this. All things equal, the greater the compounding periods, the greater the future value. Will be. Something like that. So you should know that a greater compounding period is best. when everything else is the same. Obviously, you could have, right? You could have 12 compounding periods here, 2 compounding periods here, but this might give you a higher interest rate. So you might actually be better off going with the semi-annually, right? The second option. So you would have to calculate and actually see at the end, like which one gives you more money. Okay, but all things the same, you don't have to calculate, you just conclude, right? Okay, keep going. Keep going, keep going. Something very cool, the rule of 72. I will make sure you understand this though, because some students forget that. It's an estimation tool. Okay, it's an estimation tool. It's not 100% accurate. This is page 18, by the way. Okay, the rule of 72 is an estimation tool, mostly used to estimate how long it would take for an investment to double. Do you remember that? What's that called? How long it will take for an investment to double? For something to double, that's a doubling time. Okay. It allows you to quickly estimate the time it would take for an investment to double. Okay. Given the percent interest rate, regardless of the amount invested. It doesn't matter if you invest $1 or if you invest $1 million. It would still give you that the time it takes in years, right? Something important here, don't convert percentages to decimal. You do not do that. And this is essentially the doubling time that you're finding. So if you want to find the time in years it would take your investment to double, you just go 72, that's why it's called the rule of 72, divided by the interest rate. That's just how it goes, okay? We use the same, we just move things around. We manipulate this formula to come up with this one would give you the rate, right? The rate required to double your investment. You would use this formula, which is 72 divided by the number of years. So let's say you have 20 years and you would like to double your investment in 20 years. You would just go 72 divided by 20, and that will give you the rate that you would need to find to make that happen. Don't multiply your answer by 100, very important. So rule of 72, all the rules that we've done so far, like turn your percentage to a decimal, all that goes out the window with this one tool, rule of 72, okay? So let's put it to the test. Mr. D would like to double his 250,000 secret stash in 5 years to retire early. What interest rate would he need? Answer using the rule of 72. If it says using the rule of 72, don't try something else, because it is possible, but you just use that. So it's asking for the interest rate. So the interest rate required is 72 divided by 5 years. Right? So basically you always have to ask, like, is it asking for the time or the rate to double your investment, right? So it's the rate that it's asking for. So 72 divided by 5 gets you 14.4%. And I will just make sure you understand. 72 divided by 5, I don't multiply by 100. That is just it. Okay? That's just how it goes. So this is the interest rate required. Required to achieve goal. Achieve goal. Okay? So if I were able to get an interest rate of 14.4%, somehow I would double my money in 5 years. And I will just say this, it doesn't matter, the amount doesn't matter. If I had $1, if I put that dollar in the savings and I get an interest rate of 14.4, in 5 years I would have $2 in the account. That's just how it goes, right? So verify your answer using the compound interest formula. So here, come with me. So we're going to do this one. Assume yearly compounding. What does that mean, yearly compounding? N is equal to 1, right? Yearly, it's only happening once a year. That's what N stands for, how many times a year. A is equal to, we have that secret stash of 250,000, 1 plus the interest rate that we're supposedly going to get is 14.4, which is 0.144, divided by 1. It's a little bit irrelevant, right? I don't need to do that, but I'm just showing you. And then it's 1 times, what's my time? My time frame? 5 years, right? This is the time that I'm using there. And the interest rate is, so I'm verifying. I want to see if I have $500,000 if I plug in these numbers that I was given. So it's 250,000, and this is just 1.144 to the power of 5. That gives me that. So it's 250,000 times 1.959. Is it going to double my money quite? Are you multiplying it by 2 there? Not quite, but it's almost 2, right? So you go times 250,000. So the answer is 489,857.92. Close to double, right? It's close to double. Rule of 72, estimated, right? So we estimated that it's 14.4 to double, but it turns out that it isn't quite 100% right, but it's close. So you probably need more like a 15% interest rate, right, to for sure make that happen. But we just verified using the compound interest formula, and we went from 250 to 489,800. Okay, keep going. I think I'm going to skip a little bit. Let me see. Let's do page 20. So I'm skipping 19 for now, just because I'm looking at my time and I would like you to have one of these examples. And I try to put headings down, right? Solving for principal using the compound interest formula. If the question asks you to determine the principal, right? Question asks to determine the principal, you will need to substitute and then isolate for P. Yeah. So watch this. Zach has accumulated 45,000. That is actually, you have accumulated, that's what you have. That's actually A, that's my future value. For this much time, that's T, the bank statement shows that he's earning a rate of 3.99%. This is rate. Compounded daily, N is equal to 365. How much did he start with? What is it asking for? P. It's asking for the letter P. How much did you start with? And you know it's compounding because there are compounding periods, right? So we use this formula. Plug that in. We have the 45,000. We don't know what P is. We know everything else. Rate is 399. The compounding periods is 365. And so it's 365 times 3.5. Oh my goodness, that's going to be a big power, right? You guessed? Yeah, that's right. And then just clean it up just like before. So watch what I'm going to do here. 0.0399 divided by 365. Oop, there's that. See that? That's what I'm talking about. just add 1 to this. So plus 1, it solves that problem for you. So I'm going to do one more line here. This is 1.0001, and that keeps going. And I'll just figure out the power. 365 times 3.5 here. That's 1277.5. No big deal. The calculator can handle it. So watch what I do on my calculator. I go up to that base, right? And then I raise it to this exponent, which I also have on my calculator. Right, this to the power of that, and that gives me that. Okay, so you're slowly cleaning this up. So you basically just have this all turned into 1.149 ... p. And what's the last step? Right, like this is multiplying that. So all we need to do is divide. So we go 45,000 divided by that number, and that's 39,000. Remember, we're figuring out how much we would have to invest in the first place to get the 45,000, right? Okay. Zach started with 39,135.12. So every once in a while, I ask a question like this. Remember, it's compound interest, so you have to use this formula, plug in everything you know, clean it up, and then just use algebra to isolate. Right? Okay, let me see here. The homework. I'm going to ask you to start. There's simple interest on page 22. You decide if you need that. But I'm going to ask you to go from 24, and I'm just trying to figure out what page number that is, 24, 25, 26. Yeah. So homework, page 22 to 26. However, page 22 is all simple interest. If you feel like I got simple interest, I don't want to spend more time on it, do everything else. There's some rule of 72, some of this, like try everything a little bit, and then you just go from there. I will talk about rule of 72 a little bit more tomorrow.